Part 2. This is the one that has some calculus in it. So, but it's simple calculus. Um, let's talk about a uniformly charged thin rod. Yay! All right. So a rod has some length and thickness. Usually its thickness is much, much smaller than its length. That's the whole idea of why it's a rod instead of a stump. And uh, the electric field near this rod would be something like this. So let's just get our mind on what it is we're paying attention to here. I want to draw your attention to this right here. This example is going to be about some little chunk of charge that's on the thin rod. And there's going to be infinitely many chunks identical to this one. That's what calculus does for us, is it lets us pick one thing, work all that out, and then add up all of that in accordance with the length or the volume or whatever the thing is. So we're purposely picking just one little piece of the puzzle since the rest of the pieces of the puzzle are the same. It's sort of like nobody buys a puzzle that's full of squares, right? What's the point? There's no thing to figure out on that. Okay, so just to get our bearings here, we're talking about a chunk of charge that is some distance. Oh, it's not at the origin. It's offset from the origin. Some distance away from the middle. All right. So notice also that I'm talking about a delta Y, a delta Q, and therefore there's a little chunk of the electric field. So when I say delta, yes, I still mean a difference, but I want you to think in chunks. We're chunking out this electric field by picking a representative piece of the puzzle, since they're all identical with the exception of where they're located on the rod. So in addition to those chunks having dimensions and directions, then there's this distance that it is away from the origin on Y, and the distance that it is from the origin away on X. So I'm getting, there's this right triangle business that's going to help us with the math. Those are just the basics. This vector, we're going to consider electric field at some point, x0, 0, that's what this point is here. It's out there on the x-axis, 0 on the y, and 0 on the z-axis from a 3D perspective. All right. Again, I don't know that I want you to take copious notes on this. I just want you to follow the thinking. And we just did essentially the same thing in terms of that thinking. There's the position vector r is going to be, well, what's the observation location? Okay, that's this x00 business. And what's the source? Well, the source of this delta E is this delta Q up here. And that delta Q is at 0, y 0. It's just got one non-zero component on the y-axis. And then the observation location is just at x0. We just went over that. And so we run the numbers here, and the observation distance versus the source distance, and we get this final output for our position vector relative to some chunk of charge. Then the rest of the drill. Once I have a position vector, inevitably I'm going to, since it's a vector quantity, that means I need its magnitude and its direction. And again, we're back to this Pythagorean business for the magnitude, and then applying the definition of a unit vector in the end there. So this is the reason why I said don't bother taking notes, because the math is just whatever it is. The ideas are what I'm caring about mostly, but I'm going to derive this for you anyways. That means that I can take my electric field equation. Hopefully you recognize that as the basic definition of electric field. The Coulomb constant times the charge over the distance squared. The thing that's new here is this charge here, this delta Q, I'm talking about a chunk of charge, as opposed to a particular singular charge like we've idealized so far. All right. We just found that r squared was this. Instead of just being a plain old r squared, it actually was this Pythagorean thing. We've used this a couple times, though, already in this course. We were just doing this in the homework. Okay, so this isn't the first time you've seen it in this course or in your academic life. All right, continuing. So if I take this, okay, that's all we're doing is, here's our, actually I'm just gonna, our magnitude part. And this is our unit vector part, if you remember from the last page. Exciting stuff, right? Well, looky here. This is raised to the 1 power, and this is raised to the 1/2 power. Hopefully you recall your laws of exponents from your algebra class. Same base, different exponents, multiplied, you add the exponents. So 2 over 2, or a 1 plus a 1 over 2 gives you that 3/2. That's how we went from this line to that line. So we get this interesting vector equation for the electric field of this chunk of charge. Remember, we're talking about the electric field of that chunk of charge. This part is the magnitude. The other part's the direction. So this little arrow business is because I have that unit vector. I'm not going to labor through the math for the y part, but I would have you note that what's different? Well, the y part has a y part. That's a notable difference, but it's still the same chunk of charge Q. That hasn't changed. We're still talking about that chunk of charge producing that chunk of electric field. And we're talking about it in terms of the x and y parts that describe the distance that they are away from one another. And since this is all in the xy plane, the z part ends up being not part of our puzzle, which is 0. Now, before we move on, this is sort of important. A little chunk of charge on a rod, we actually don't know how to count individual chunks of charge like that on an object. Here's what we can actually count. What we can actually count, I can take an object, and I can put it in a box that's a charge counter. Okay? Please pay attention. And I can count the total charge on something. That's what I can actually count. And then given how long something is, or what its total area is, or maybe what its total volume is, then I can work out a charge density. And that's something that I can actually count because it's in terms of the length or the area or something like that. Okay? So looky here. What is this right here? Delta Y. That's actually I guess the height of this chunk of charge I'm paying attention to. I don't know how big or small that chunk of charge is. It's a unit. There's infinitely many of them in the length of the rod. So this is a fraction, a delta Y per L. So remember we have this rod, and there was this chunk of charge delta Q. Okay. And this was my delta Y length. Okay, that's how big this delta Q is. All right. And then the length of the rod, would just be some length L for the rod. So what fraction of delta Q relative to the whole length? Because what I know the total charge on the rod. That's something I can actually get. I can actually get total charge on the rod, but in order to get what the little chunk is, I need the linear charge density. Okay, so this right here is that linear charge density. Charge per unit length. And it allows me to talk about that chunk of charge that I've been idealizing for my model from the beginning in terms of how tall it is. Because a delta Y is something I can add up. I can actually add that up. I can measure that length. I can measure total charge on the rod, but I can't measure a little piece of charge on any object. We don't have that toy. So we have to work our way around that mathematically. Plus, then the calculus of it, for those who care, you have to do it along a length. You have to do it along a quantity that's integrable, differentiable, if you will. All right. So we run through all that rigmarole, and we get these interesting equations. The chunk of charge in the x direction can be thought of in terms of what I would expect on an electric field. So I'm going to highlight in blue the stuff that I expect. That's a kq per r squared-ish sort of thing. That's inconsistent with what we're used to on the field, though it's been modified because of the geometry. But then the charge density piece of the puzzle comes in that regard. And then we have the position here, and then the same sort of structure, but for the y direction in the second part. So the chunk of the electric field due to the x direction, and the chunk of the electric field due to the y direction after I figured out this charge density business. So some of your problems will have a charge density discussion because the equation requires charge density. more math that I'm not expecting that you write down because I'm not going to ask you to derive it. But I do want to finish the deal um, in terms of how we sum things up. Because if you remember, we purposely picked one little piece of the puzzle because all the pieces are the same piece. And if I figure out how it works for one piece, I figure out how it works for all the pieces. And if I follow the superposition principle, it's the sum of the parts equals the whole. That's the short, simplified version of it. So now, sum of all the parts. That's what that would be. If I sum up all of the chunks of the field in the x direction for every chunk of charge at every delta y, okay? Or I guess that should be delta x uh, in there. And same thing for the other one here. It's just a summing up process. Now, that wouldn't be easy to do if you're counting them one at a time, really small. So that's why God invented calculus. Well, he invented Newton, invented calculus, all right? This whole limit process. So since most of you have had calculus 1, in some classes, everybody, you recognize what that means, and this summation symbol is going to turn into an integral. I'm not going to do the calculus, or not all of the work, but it all comes down in the end to evaluating it this way go from the top end to the bottom end. And so that's how we end up getting away with this sum. We went this is what that is, basically. All right. Those of you that had the calculus, you know what that is. Again, I'm not asking you to produce all of that, at least in this class. All right. So if it's the case, so we had this ugly part from the last piece that I glossed over. That looks like a royal pain in the rear to deal with. Yeah, it is. But thankfully, if my length, if I'm way farther out than the length of the rod, then this thing that we got to do earlier, that means that this basically goes to 0 effectively. It's so small compared to r that its square added to the square of r, you can't tell the difference. All right, so this thing gets simplified again. And looky here, all of that work. And what did we find? It's the same as the electric field for 2 charged particles. But we wouldn't have expected that. That's the point. That wasn't what we expected, but it is the way it is. Now, if my observation location was too close to the rod, then this breaks down. If that r much, much greater than L is not true, then I don't get this. I get something else that's more complicated, which we're not going to worry about until now. What if L is bigger than R? What if the rod is infinitely long, so to speak? Well, then that basically means the R squared part is meaningless, and I get this. That's also a relatively simple equation. But the point here is well, one, nobody would imagine this result on screen right now. Just, oh, obviously it's that. All right. But we also wouldn't have thought that the other side of the coin was as simple as it ended up being. So it took a lot of non-simple things to obtain a simple thing. That's the way science goes. So the trick here is if you get a problem, either you'll be told that these distances are much, much greater than or less than one another, or you won't. If you're told it, then you know which equation to use. If you're not told it, you have to make a judgment. Is 1 meter much, much bigger than 1 millimeter? Yes. I'll use the equation that goes with that. But is 1 meter much, much greater than 0.9 meters? No, I go with the other equation. That sort of thinking. Which means, all right, what about a ring? So this gets really complicated. So again, pause on the note taking. Just want to get the idea. Started with a rod because, well, it's simpler because it's straight. And a ring, well, what's a ring? It's a bent rod, right? So let's remind ourselves that once again, I'm dealing with a chunk. But instead of this chunk having a measure like delta y, I'm going to give it a measure of delta theta. Because guess what? When things are round, angular displacement is a better measure than actual length. That would take us back to the end of last semester to recall that. All right. So now I'm going to deal with delta theta as a length as opposed to a delta x or y or z or whatever like we were in the last example. And of course, it's constrained by some radius r. And it would have this whole rod. There's a total charge on the rod. Okay. So this picture was obviously made with Python. Hope you recognize these little chunky, blocky doohickeys. This total chunk of electric field, meaning due to this chunk. So if you can still see this in 3D, this is the resultant vector, and it has, an x part, a y part, and an out of the page z part. Math on this one gets complicated, as you might expect, because not only am I dealing in 3 directions, but I'm dealing with angles. Again, I'm not expecting you, nobody's going to have to derive this on the test. You'll just get to use the last line of the equation for your math. We've been around this block a few times. All right, so let's just highlight literally a few things. Old news that the position is observation location minus source location. Hoping that you guys remember that an x part angularly would be an r cosine theta, and a y part converted would be an r sine theta. Those were some formulas you would have used in trig. And then we obtain an r vector that has its angles and lengths that constrain those angles. Yay. So now that I have that r, guess what I can do? I can get a magnitude of it. I can get a unit vector version of it, which means I have magnitude and direction for that part of the. That's what's going to pop here next. Again, I'm not asking that anybody bother with this just yet, but those are the way that works out. All right. What in the world is this? All right. Here, this would be just basically our basic electric field idea, kq per r squared. So this is our basic idea. Except it happens to be the case that our r squared was a little more complicated, namely that complicated. So sorry for the high-tech terminology, but I want to chunk out the thinking and the mathematics as well as the actual charge quantity itself. Then coming back to the charge density idea, I can't actually measure delta Q. I can measure total charge on the ring, and any particular delta Q would be this fraction of the total charge. And the fraction in this case is a little chunk of angle out of the entire circle angle of 2 pi. So I still have a linear charge density, except it's on a circular path, linear charge density. All right. Then here we have our vector. All right. Will consist of a magnitude, namely this thing here, and a direction, which we computed on a different screen. So again, starting from our basic, going through a not so basic thing. Ugh. Aren't you glad you didn't have to do all that math? All right. So this is, the way it would get computed, say in a, if this were related to, say, an imaging technology or something like that, somewhere under the hood, this equation is lurking, or some variant of it. These values are fixed. These changes are coming in from sensor components in the MRI or the CAT scan or the you fill in the blank for the technology. As sensors that are picking up these sorts of things as the device does whatever. So we go through, math, simplifying, etc., and we get these answers. So for those that are interested in the calculus, a chunk of field dependent on this chunk here, those become differentials in calculus land, which lets us add things up with respect to that variable, and we get, in the end, an equation that's this here is obviously better to look at than this rigmarole here. So eventually we go through a bunch of math land trials and tribulations, and we come up with this thing. Then just notice again, what do we have? We have a K, a Q, and we have our distance to an unusual power. Thing that's different about this electric field, besides that it's not an inverse square, is that I also have this dimension attached to it as well. Slightly more complex than the dipole equations, and definitely a little more complex than the basic 2-point charge model. The thing that I want this group to notice is that fundamentally the electric fields have the same basic structure. There's charge and there's distance, which we knew that from the first sticky tape lab, basic Coulomb law stuff. You'll see this kind of pattern throughout all of science, where the geometry of the situation, meaning how the objects are situated, how the machine senses or does its thing, will always produce variations on the theme. When you take a statistics class, okay, you'll learn to do standard deviation several ways. Fundamentally, they're all the same, even though they have some slight differences computationally. They're still measuring the same kind of thing in basically the same way. So math, physics, science, these patterns persist even though they have get dressed up differently. All right, so Uh, that's the thin ring version of a